Okay, so we're on page 609. We're doing question number 4. Okay, question number 4. 2 loops of wire are moving in the vicinity of a very long straight wire carrying a steady current as shown in the figure. So the figure looks like this. There's the wire. It's supposed to be straight up and down. There's a loop that's moving this way. And here's another loop that's moving that way. And the current, we're told, is moving here. The current in the wire is going that way. And we are asked, what is the direction of the induced current in each loop? Okay, what's the direction of the induced current in each loop? So again, the induced current is based on the change in flux, right? The change in flux as the loop moves through the magnetic field. So first, what is the magnetic field? Based on this current that's going up and the right-hand rule, the magnetic field goes into the board on this side of the wire. Right? And as we wrap our fingers around, it comes out of the board on this side of the wire. Coming out of the board there, right? I didn't draw it very well, but the further away from the wire you get, the lower the density of the magnetic field lines in each direction, right? And that's the key to this problem or this question. We can visualize this loop of current moving up here. As it moves, because it's not going anywhere away from the wire that's producing the magnetic field, there's no change in flux, right? There's change in location, but there's not going to be any change in flux because the density of the magnetic field, the strength of the magnetic field, or the density of the magnetic field lines at this distance from the wire is the same the entire length of the wire. So for this loop here on the left, there's no change in flux, therefore there's no current in the wire. Right? With this one, there is a change in flux. As it moves away from the wire, the magnetic field that it's in gets weaker. So there's a change in flux, and therefore there is a change in, there is an induced EMF and an induced current. As this moves along, so now doing my right-hand rule, as I move this from here to there, there's less magnetic field lines going through the loop this direction. So it's going to induce a current that will replace that lost magnetic field strength. So as if you could imagine this loop now over here, I'm going to draw it bigger. It's now over here. I drew it bigger. It's the same size. I drew it bigger so it can fit my hand. I need to add more magnetic field lines going into the loop because there are fewer as it moves away, which means the current has to be my thumb. So at this point, the current's got to be going that way, which would be clockwise, right? Clockwise around the loop is the induced current. Okay, we visualize that, right? This is getting weaker. So I got to replace that magnetic field with the induced magnetic field, which means my thumb is going up on this side of the loop or in the clockwise direction. Okay. The next one I picked out was problem number 3 on page 610. I'll try and draw it. We have a bar magnet, north end, south end, and a loop of wire. This is going to be the hard part. A loop of wire that looks like this. And a resistor down here at the bottom. And we're told it's the north end of the north pole of the magnet is being inserted into the coil. What is the direction of the current going through the resistor? So now I don't know how well you can see my drawing, or you can see, hopefully you're looking at the drawing in the book. So like this is, that wire is in the back. These wires are in the back of the loops here. Right, so each loop, the left side of each loop is the front of, and the right side of each loop is in the back. I'm trying to draw 3 dimensions in 2. So as we move the magnet into the coil, we're adding extra magnetic field lines this way, right? Because the north, let's draw it up here. So it's actually at that level. Magnetic field lines come out of a north pole. So now as I push it through the coil, I'm pushing more magnetic field lines this way. So the induced current is going to produce a magnetic field that's going to go back against that. So again, picking out the loop, my magnetic field line's got to go this way in any given loop. The front of that loop has to have the current going up, or the back, right? If there's my current, my loops, right? My magnetic field line's got to go here. So the way I see it, if I'm visualizing it, is the front of the coil has to have the current going up. So that means the current's got to be going to the left through the resistor. Okay, again, the induced magnetic field has got to resist or oppose the change in magnetic field due to the motion of the magnet and or the wire. Good? All right, I picked 3 other ones to, again, just as general questions that I thought were appropriate for what you need to be able to do. The next one was number 9. Again, and these are all just conceptual. What's the direction of the current? So number 9 has 4 different scenarios. Scenario A has an increasing current going this direction through this wire, and there's a loop of wire here. What's the direction of the induced current? So again, my magnetic field right-hand rule tells me that below the wire, the magnetic field is out of the board, out of the board, right? And if it's an increasing current, there's an increasing magnetic field change. The strength is going out of the board is greater, so the induced current's going to oppose that increase. So it's got to have magnetic field lines going into to oppose the change. So my thumb, if I'm on this side of the loop, inside the loop, I'm opposing it. My thumb is going down here. That's telling me my current's going clockwise in part A. Right? In part B, this time the current, which direction is the current going? The current is going to the right and it's decreasing current. And the loop is above it. So again, right-hand rule tells me the magnetic field lines of the magnetic field produced by the wire is out of the board, above it. If it's decreasing, that means those magnetic field lines are, the magnetic field's getting weaker. So the induced current's got to strengthen the magnetic field to replace the loss. So using my right-hand rule on the right side of my loop here, I got to replace those lines. So again, this time my thumb on this side is pointed up. So I have an induced current that's counterclockwise. Right, in part B. In part C, the current is down the board and it's decreasing. And the loop is to the left. So right-hand rule tells me into the board is the magnetic field produced by the current. Decreasing means that that's going this way is less. So my induced current's got to replace it. So on, again, on the right side, I got to add more going into through. So my thumb is pointing this way. So I'm looking at a clockwise induced current. And finally, in part D, the current is up. The current is constant. And the loop is on the right side. But this is the key word. It's a constant current, which means there's no change in magnetic field, which means there's no change in flux, which means there's no current going through the loop. Right? No current, no induced current in the loop. Okay? All right, finally, it's numbers 11 and 15 are the other last two that I picked out. Right, which actually have using the formulas. So in 11, a magnetic field's perpendicular to a circular wire, which has a loop of 12 centimeters in diameter, and it's changed. The magnetic field is changed from positive 0.52 Tesla to negative 0.45 Tesla is the change in the magnetic field, where positive means the magnetic field is towards the observer, out of the board. Negative is into the board. And right, so it starts off like this. And it ends up the other way, the opposite. And we are asked to calculate the induced EMF and then to what direction does the induced current flow, right? So the induced EMF is the change in flux, delta flux over time, right? I feel like I'm missing a formula. I'm missing a letter in my formula, I feel like. Something doesn't feel right to me there. Nope, that's correct. And change in flux would be change in magnetic field times area over time. Right? So in terms of direction, it was this way, it's now that way. So I got a resisting change. To me, I'm adding more magnetic field lines this direction. So my current has got to go counterclockwise. And to find the EMF, I'm just going to substitute in there. The EMF would be change in magnetic field, final minus initial, negative 0.45 minus 0.52 Tesla, times the area, which is a circle with a diameter of 12 centimeters. So pi r squared 0.06 meters squared. Does it give us a time? In 180 milliseconds, all over 0.180, right? Change in Tesla, change, this is Tesla, this is magnetic field, or change in magnetic field. This is area, and that's time. Right? Whatever that works out to be. Good. I'm not going to finish pushing buttons because that's just pushing buttons. You guys can handle that simply enough. Like I said, I just kind of picking out a few that I thought was a good sample representation. Which brings me to the last one that I picked out, which was number 15. Okay. Number 15. We are given a situation where we have a magnetic field that is into the board. We have a rectangular loop of wire. That looks like that. Moving in that direction. There's our picture. And this length of wire is 0.75 meters left back that way, and it is 0.35 meters this way. Right? That direction. So we read the problem. Part of a single loop rectangular wire with dimensions as shown is situated in the region of uniform magnetic field of 0.55 Tesla. Total resistance of the loop is 0.23 ohms. R 0.23 ohms. Calculate the force required to pull the loop from the field. What force do I need to pull the loop from the field at a constant velocity of 3.2 meters per second, 3.4 meters per second, I'm sorry. And what is force? What force do I need to pull it? Okay. All right. So I like this one because we can do, all right, we can, we have to use a couple of different things, right? The fact that it's moving through here, we know that that's going to induce a EMF, right? Because it's going to change the flux, because this, to the right of this, there is no magnetic field. So it's going to reduce the magnetic field going into the board as it moves, which to me means that the current has got to go in a clockwise direction. The induced current's got to go in a clockwise direction. we got to find how hard we have to pull. Right? So, using the formulas that we have, the force, where I'm going to put this, the force, my marker is dying. I hope it's dark enough for you, is equal to the magnetic force is equal to ILB, right? The current times the length of the wire times the strength of the magnetic field. The length of the wire is this length of the wire, right? The long lengths don't matter. The long lengths in this scenario do not matter. Right? Because yes, there is as it moves through the magnetic field, there is a force on it, but the force, let's see if the current is going, he said it's clockwise, right? So here, the current's going clockwise. The force on the bottom wire is down, where the force on the top wire is up, but those two would be a net force of 0. So these lengths don't matter because the forces have the same current, the same length, and the same magnetic field. So the vertical forces, the way it's drawn on the board, would cancel. So the only length that matters is this one, right? And again, the current's moving up, the magnetic field's into the board. So the force that this length of wire is experiencing is to the left. That's why I have to pull to the right to balance it, to pull it at a constant speed. So the magnetic force is the current times the length times the magnetic field. And we know that the induced EMF is equal to change in flux over time, which is, in this case, current times it's magnetic field times length of the wire times the velocity of the wire. And current, because this is the voltage, it's an EMF is a voltage, so current is voltage over resistance. So I is equal to voltage over resistance. So I can make this substitution into this formula and solve for force. F equals I times L times B, which simplifies to B squared L squared V over R is the force. Okay, I like that formula or that one because it makes us apply a couple of different ideas that we already know and put them together. Then we can just substitute our numbers in. We know the current, we know the magnetic flux, we know the length is 0.35, we know the velocity was given as 0.34, and we know the resistance. We can substitute the numbers in and push the buttons easily enough. Okay, but I like this one, like I said, because it asks you to use a couple of different things that we know and put them all together. All right. Any questions on any of the ones that I picked out? No one stopped me as we were going, so I'm assuming you were following along. If no one has anything else before I turn off the recording, does anyone have anything else that they want to talk about, ask about? Okay. All right, so I'm going to stop the recording.